Today I'd like to show everyone a differential equation that I used in my differential equations class. And the whole class kind of found it quite hard, but also interesting at the same time. So I thought it might make an interesting video. So to put it into perspective, this was at the tail end of studying exact differential equations, when we solved exact differential equations by finding an integrating factor. And this integrating factor transformed a non-exact differential equation to an exact differential equation. So if you want to learn more about the basics of solving these types of equations, I've got a whole course that's being built on my second channel Math Major. You should be able to find a link in the description. Okay, so let's see what we have. So our differential equation is a cosine xy minus y sine xy plus b cosine xy minus x sine xy, y prime equals 0. And I've written in this differential equations form instead of in the differential form, which is typical for exact equations, just to keep it looking a little bit more like a regular differential equation. Okay, so like I said, we're going to use the method of integrating factors to turn this into an exact differential equation. And that means we're going to take this entire thing and multiply it by an integrating factor. And this integrating factor will be a function of x and y, but it won't just freely be a function of x and y. We will assume that it's of the form p of x times q of y. And the big theory behind these integrating factors is really that it's kind of quote unquote easy or reasonable to find them if they have a nice form. But if they're more general, it's like pretty much impossible to find them. So when you study them in class, you generally study them in certain like forms, like for instance, this form. Okay, so let's do that. We're going to multiply this entire equation by p of x times q of y. That'll give us the new differential equation, p of x times q of y times all of this. So I'll write that as a cos xy minus y sine of xy. Great. And then I'll also put my p of x times q of y times the rest of this stuff. And I'm splitting this up into the part that's multiplied into y prime and the part that's not, because we want to impose the exactness condition, which we'll do in just a second. Okay, so let's repeat this. We have b times cosine xy minus x times sine of xy, y prime equals 0. So just to reiterate, all I did was multiply everything here by our hopeful integrating factor, which, as I said, we assume is of the form p of x times q of y. And now we'll impose the exactness condition. So let's recall the exactness condition is that everything that is not attached to the y prime and everything that is attached to the y prime are related by taking the partial with respect to y of this term and the partial with respect to x of this term and achieving equality. So if you check that for the original differential equation, you will not achieve equality. But if you set it up with this unknown integrating factor, you'll see that we will get some sort of equations that we can solve for the integrating factor. Okay, so anyway, let's take these two derivatives. But before we do that, let's change this from green to pink so we have a nice color coding here. So this is the partial with respect to x. Okay, so let's do this partial with respect to y first. So I'll have to use the product rule here a couple of times. So I'll have p of x q of y times the partial of all of this with respect to y. So that's going to give me, let's see, we'll have negative a times x times sine of xy from taking the derivative of this term. But then taking the derivative of this term will require the product rule. Taking the derivative of y is 1, leaving us with negative sine xy. Then taking the derivative of sine xy will give us something like minus x times y cosine of xy. Okay, nice. And so that's what we get from taking the derivative of the stuff inside the parentheses. But then taking the derivative of the stuff outside the parentheses will give us plus p of x, and then what I'll call q prime of y, times everything that's already in there. So that'll be a cos xy minus y sine xy. Okay, great. And now let's put a big green box around that to say that is the partial of that term with respect to y. Okay, nice. So now we'll take the partial of this term with respect to x and see what we have. So we'll start with this p of x times q of y, and then we'll have the partial of the inside stuff with respect to x. So let's see. That'll give us minus b times y times sine of xy. So that'll be from taking the partial of this with respect to x, and then this will split up using the product rule. We'll have minus sine of xy, and then minus xy, the cosine of xy. Okay, nice. Then we need to add that to what we get from taking the derivative of this p of x times q of y with respect to x. But since p is only the function that depends on x, y only depends on y, that gives us p prime of x times q of y times what was already in here. So that's going to be b cosine of xy minus x times sine of xy. Okay, so now let's put a box around that. That's what we get from taking the partial of all of that stuff with respect to y that is pink coded. Okay, so now we want to impose equality here, because imposing equality here is imposing the condition that this is an exact differential equation. And now we want to start canceling things. So let's notice we've got a p times q times sine of xy on both sides of this equation. So we can go ahead and cancel those out. So I'll cancel this sine of xy here, and also this sine of xy here. Okay, good. Then we also have an xy cosine xy on both sides of the equation. We'll cancel that here and that here. And after we've done all of that, we no longer have what I'll call like terms. And after we've done that, we don't have any like terms to cancel. That being said, we have some things that look kind of similar, and that is this p times q times a function and this p times q times a function as well. So the logical thing to do here is to move everything with a p times q to one side of the equation and everything else to the other side of the equation. So what I'll do is move this p times q times ax sine xy to the other side of the equation. So that'll leave me with p of x times q of y, and then we'll have ax sine of xy, and then minus by sine of xy equals. So just to reiterate, that comes from taking this term right here, moving it to the other side of the equation, so the plus turns in, or the minus turns into a plus, and combining it with this term right here. Okay, nice. But then after that, we'll have to move everything connected to this p prime q to the other side of the equation. Because if you recall, we're kind of trying to get this p times q by itself, and that's a p prime times q. Okay, nice. So this p times q prime is already okay. It's on the correct side of the equation, keeping in mind that we moved that over, and we will eventually move this over. So we can leave this as is. So let's do that. We have p of x times q prime of y times a times cosine of xy minus y times sine of xy. So that's everything attached to the p times q prime. Now let's have everything attached to the p prime times q. So we'll have p prime times q of x will be equal to this, but with the signs changed. And we know it has the signs changed because we moved it to the other side of the equation. So that'll leave us with x sine of xy minus b times cosine of xy. So like I said, just by flipping the order of subtraction there. Okay, and now we have the following equation that needs to be imposed. But let's maybe bring that up here, and then we'll move on. Hey everyone, before we finish this video, I'd like to take a moment to thank our patrons. The channel is possible because of their generous support. We'd like to turn off the ads on my second channel, Math Major, but to do so, we need to reach our goal of $1,000 per month on the Patreon. This will allow more people to access a higher quality experience and spread ad-free math education. So if you can chip in even a couple of bucks to help us reach our goal, go to patreon.com/michaelpennmath or click the link in the description. If you can contribute $10 or more, you'll have your name in the credits at the end of each video. And if you can't contribute money, then please share and like this video. It really does help. Also, if you haven't subscribed to the channel, but you've made it this far, you should go click the subscribe button. Okay, back to the video. Okay, so this is the result of the last board. We've got p of xy times this function, p times q prime times a function, plus p prime times q times a function. But now we'll do this trick which is typical for finding these types of integrating factors, and that is we'll divide by p times q. This may seem like a non-necessary trick, but it actually helps quite a bit because it really condenses the dependence on x and y. So let's see, if we divide both sides by p times q, this right-hand side now looks like ax sine of xy minus by sine of xy, because we've just removed the dependence of p times q. Then if we divide this term, p times q prime by p times q, that gives us q prime of y over q of y. Notice the p term cancels, and then we'll bring this down so we have a cos xy minus y sine of xy. Then the same sort of thing happens with the other term. We divide that by p times q, the q's cancel, and we're left with p prime of x over p of x, and then we'll have x sine of xy minus b cosine of xy. Okay, great. And now what we'd like to do is look at over here on the left-hand side of the equation, which has no unknowns. The role of a and b are just arbitrary constants. They're not unknowns. And see what's dominating the behavior of this left-hand side, and see if we could tweak the values of q prime over q and p prime over p in order to get it to match what's happening on the left-hand side, or what's dominating the left-hand side. Okay, so in my mind, there are two functions that are dominating the left-hand side. Well, there are only two functions on the left-hand side. But one of them is this a of x sine xy, and the other one is this b of y sine xy. Or maybe more generally, we have this y sine xy and this x sine xy, and then one of them is attached to the constant b and one of them is attached to the constant a. So in my mind, that motivates us to extract the coefficients of x sine xy and y sine xy from both sides of the equation and see where that leaves us. Okay, so I'll put this orange box here to say that we're extracting the coefficients of x sine xy from both sides. So that'll leave me with a on the left-hand side. Then what do we get on the right-hand side? Okay, well there's no x sine xy here, but there is here, and its coefficient is p prime over p. So we've got p prime of x over p of x. So perhaps that's our value for p prime over p, and we can take that value and figure out what p is, but we'll wait to do that. Okay, so now let's see what's happening with the y sine of xy from this yellow underline. So the coefficient over here on the left-hand side is negative b. The coefficient over here on the right-hand side is negative q prime over q. So canceling the minus signs, that gives us b equals q prime of y over q of y. Again, another fairly simple differential equation to solve. But before we solve these differential equations, let's just check that if we set p prime over p equal to a, and q prime over q equal to b, that everything works out. And in fact it does, because if we set those things equal, as I just discussed, these two terms, which I'm doing in pink overline, which are the leftover terms, are both a times b times cosine xy, so they will cancel. So let's put that, we'll say that these cancel with setting these two equal to these numbers a and b. So that means these values for p prime over p and q prime over q, in fact, will change this to a exact differential equation. Remember, all of this trickled down from our desire to change this into an exact differential equation. Okay, so now let's solve these two little baby differential equations for p and q. So this gives us p prime of x equals a times p of x. But what kind of function do we have where we take its derivative and we get a multiple of it? Well, I mean, this is a fairly intense differential equation, so perhaps you've already seen this differential equation. We get p of x equals a constant times e to the ax. But in fact, here we can take that constant just to be the number 1 because we're multiplying an entire equation by this, and multiplying by a constant doesn't really change anything. Okay, so there we've got our value for p of x. Now let's see what we can get for q of y. So this gives us q prime of y equals b times q of y, which means that q of y is equal to e to the by. So that's good. So now putting this all together, our integrating factor, which you might recall is the product of p of x and q of y, is equal to this e to the ax times e to the by, which we could put together if we wanted to, but let's leave it like that. Another thing that I'll point out right now is often this integrating factor is called the function mu, so let's put mu here to be this p times q. Okay, so now what I'll do is take this result where we have derived the appropriate integrating factor and multiply it into our original equation, put that result here, and then we'll finish it off. Okay, so we've done it. We calculated our integrating factor mu, which was p of x times q of y. Now we're guaranteed that when we multiply our original differential equation by this integrating factor, we now have an exact differential equation. But let's recall from the theory of exact differential equations that since this differential equation is exact, we can find an f of x, y, well, an f of x, y, where the partial with respect to x of that f of x, y is equal to this green underlined thing, and the partial with respect to y of this f of x, y is equal to this other green underlined thing. And furthermore, our solution is implicitly described by the equation f of xy equals a constant. Okay, so again, this goes back to just the theory of exact differential equations. Again, if you want to learn more about that kind of from the basics, go check out the second channel. Okay, so what does that mean? Well, that means we need to either start over here or start over there and take the antiderivative with respect to x or y. Let's maybe start over here. So this means that f of x, y will be the antiderivative of this green underline with respect to x. So since this e to the by doesn't depend on x, I'll bring it out. And then we'll have the antiderivative of e to the ax times a times cosine of xy minus y times sine of xy, like I said, dx. Okay. But now what's the antiderivative here? Well, I'm not going to go through all of those details because this video is quite long. And this is going to require almost 20 minutes on its own to find the antiderivative of this. There's quite a few tricks that go into this. So that being said, I'll just jump to the answer. Again, this is like in a prerequisite for a differential equations class, so I don't feel too terrible about it. But what you end up with this antiderivative is e to the by, which comes down from here, and then e to the ax, and then the cosine of xy plus a constant, but this constant will be with respect to y. Sorry, a function with respect to y. Now we need to figure out what that function is with respect to y, and we do that by completing the loop. So what we'll do is take the partial of this with respect to y and then compare what we get. But the great thing here is if we take the partial of all of this with respect to y, we achieve exactly this function right here, which means the partial of g with respect to y is indeed equal to 0, which means we might as well just take g of y to be equal to a constant. But all of that leads us to the very important fact that our final function, capital F of x, just can be taken to be this brown boxed equation here. So in the end, since that's our capital F of x, we could rewrite that as maybe e to the ax plus by, pushing those exponentials together. And then we'll have cosine of xy equals a constant. And that would be maybe a nice final way to write this as an implicit solution. And you might say, well, can I solve that explicitly? And I think you can, but I think maybe it's not super worth it. What I would maybe suggest if you wanted to solve this explicitly for y, it would be something like this. We would use the fact that cosine of xy equals the real part of e to the ixy. But I don't really think it's super important to do that. Notice we'll get imaginary numbers into this, and I think your explicit solution will look like it involves complex numbers, whereas it really doesn't. Okay, so I've done lots of interesting big differential equations on the channel. There's one on the screen right now that you might want to check out, and that's a good place to stop.